Good day, ma'am. I'm Patricia Marquez, a member of Group 2, and today we're about to present our case study entitled Maintenance Philosophy for an Unmanned Platform, a case study for an offshore wind substation. Our members includes Erica Clarice Pral, Angela Faye Ilagan, Gail Francesca Manalo, I myself, and Leslie Samuel Ivan Onda. To introduce our topic, offshore wind power, also known as an offshore wind energy, is energy that is obtained from the force of the winds at the sea, transformed into electricity, and supplied to the onshore electrical grid. Offshore wind energy is an infinite, continuously renewable energy source that produces no dangerous greenhouse gases during the process of turning wind into electricity. Next. Offshore wind generation climbed from 8.5% in the second quarter of 2021 to 11.2% in the second quarter of 2022, according to Energy Trend data from the Department for Business, Energy and Industrial Strategy or BEIS. The energy sector is experiencing a ton of opportunities for increasing productivity and cutting costs associated with asset operation and maintenance due to digitalization, automation, and autonomy of offshore substations. Due to low margins and intense competition for the offshore wind business is particularly cost sensitive. Therefore, it is essential to decrease the levelized cost of energy by decreasing capital operations and maintenance costs and increasing electrical energy generated. For the main problem, Gil Francesca Manalo will introduce it.
For the main problem of the case study, substations are designed to run unattended for a limited amount of time. The vast enormity of the structure makes navigation and cost challenging. As such, huge projects must also have lifts, cranes, boat landings, helicopter decks, and lodgings. To deal with the necessity for expensive and hazardous lifting vessels, self-installing and lifting concepts have been devised and implemented into operation. Next. The primary concern is how will that work if wind energy practitioners decide to develop a maintenance philosophies from the traditional maintenance philosophies such as corrective, preventive, and design out, alongside the emerging maintenance philosophies which are condition, predictive, and prescriptive. Planning for maintenance in an offshore location is more challenging, therefore with the goal to determine the maintenance requirements and meet the intended operational profile. Companies have been looking for a maintenance philosophy that can be more cost-effective. In fact, industrial practitioners are keen to use maintenance notes, condition monitoring systems, predictive analytics, and prescriptive analytics to prevent failures by designing out failures. Examples are using gas-insulated transformers instead of oil-insulated ones, and detect potential failures and predict remaining useful lifetime. Next. For the analysis of the issues, employing a fundamental case mechanism, this section will explain how to implement the DIP maintenance philosophy. As described in the preceding scenario, three actions must be taken to implement the DIP maintenance philosophy, which are system boundary and failure mode analysis, and study of maintenance philosophy. For our next presenter, we have Samuel Ivan Anda.
For the system boundary analysis, the Figure 1 presents the diagram of the system prior to the implementation of the new maintenance philosophy. As mentioned already, an unmanned offshore substation contains the high voltage and medium voltage electrical components for transforming the 33 kilovolts power supplied by the wind turbines to 150 kilovolts for the export to the onshore grid. The substation system is depicted schematically in Figure 1. It has been demonstrated by the industry that cooling the substation is necessary to extend the life of the equipment and reduce the losses of electrical power supplied into the network. Figure 1 also provides a schematic representation of our case study's cooling system, analyzing the major components of the apparatus including the cooling system's consumer, pump, heat exchanger, and expansion tank. This case study is delimited only to the cooling system where the three apparatus are analyzed in depth: the pump, the heat exchanger, and the expansion tank. Next. And for the failure analysis and DIP study, the concept that has been presented for the DIP maintenance places an emphasis on the necessity of doing a high-level failure analysis as well as critically and consequence analysis. We place an emphasis on a high-level analysis because not all stakeholders, such as vendors, operators, contractors, will be engaging, and it is possible that specific information will not be attainable during the period of the concept research in which we are currently engaged. In this stage, we are going to investigate the failure modes that are the most critical, considering the local and global effects and consequences of the primary components of the system we have chosen. A failure mode and effect analysis, or the FMEA, which has been created and displayed in Table 1, has been done to gain an understanding of the significance of these components. Also, the IP research worksheets extend the FMEA studies into maintenance philosophies and their capacity to prevent the certain failure modes. To acquire the best result from the DIP study, you need an in-depth understanding of the system and an overview of the condition and monitoring and equipment control technology. Thus, this investigation should include varied expertise. Process engineers can explain redundancy for pumps and heat exchanger in this case study. Next. And for the table 2, it presents the DIP study for an offshore substation. Table 2 contains an analysis of the failure modes of the three primary functions, which are pumping, cooling, and handling the thermal expansion. Since this is an investigation of failure at the equipment level, failure modes of the components and sub-functions are not being taken into consideration currently. For instance, for instance, the pump may be unable to start or it may experience a spurious halt because of mechanical failure. These failure modes will prevent the pump from performing its roles of circulating the cooling medium, which will result into the shutdown of the cooling system. By using a redundant pumps, it is possible to avoid the shutdown that would otherwise be principal global effect of such failure. Since the breakdown must be rectified promptly and cannot be regarded as postponed occurrence, maintenance is not viable choice. As a result, this design team believes that the optimum maintenance philosophy is to have a redundant pump that is outfitted with the CMS to enable the prescriptive maintenance. This will assure that no further maintenance will visit be required. In addition, prediction can be made, but doing so is not advised. And while designing out problems at the system level is possible, such as possibilities can be investigated in the equipment level. Next.
For the figure 2, it presents the schematic representation of the system after the new maintenance strategies have been implemented. As illustrated in figure 2, the traditional atmospheric expansion tank is replaced with a pressurized expansion tank covered with a gas, which is the nitrogen blanket, to eliminate the danger of cooling medium contamination caused by exposure to air. This case study aims to demonstrate how the DIP study is conducted and what its results looks like. Evidently, the results of the DIP study may differ between two groups or experts due to their varying levels of expertise and knowledge. However, as demonstrated in this case study, conducting a DIP study provides the opportunity to improve the maintainability of an asset based on organization's available knowledge and experience. Next, for the big picture analysis of the DIP maintenance philosophy, innovation is the key to progress, but every innovative technology or method has the potential for negative consequences. In addition, it is essential to evaluate and elucidate all dependencies surrounding for a new technology or approach in order to maximize its potential for positive outcomes. To gain a comprehensive understanding of the proposed maintenance philosophy, we have utilized the Table 3 Innovation Big Picture Matrix, an effective instrument for this purpose. The time frame of the matrix is determined by the average substation platform lifespan of 25 to 30 years. Long term refers to the last 10 to 15 years of a substation's life. Next. So table 3 presents the innovation big picture of the proposed maintenance philosophy. So in the early stages of development, the platform faces infant mortality failures and significant uncertainties. Due to designing out severe failures and adding redundancies, the suggested maintenance philosophy increases short-term availability. Since it uses low-frequency maintenance cycles, it should be highly available and cost-effective. This maintenance philosophy relies on the optimum technology for a given purpose and equipment reliability. Due to limited space on offshore platforms and high capital costs, redundancy cannot always compensate for equipment reliability. Thus, high failure equipment prevents low frequency maintenance. However, this maintenance philosophy requires substantial investment in the latest technology, extremely reliable equipment, and powerful sensors and data processing systems. Digitalization and sensor use also raise short-term false alarms. Therefore, a high rate of errors might be seen in sophisticated and complex maintenance management system during the first few years of operation. Next.
Next, for the conclusion, what limits the benefits offered by modern maintenance technologies are covered in this study. This demonstrates the value of researching various maintenance philosophy during the design and development process concept study. The maintenance philosophy benefits are mostly focused on the substation medium phase. Preventive, prescriptive, and corrective maintenance maintain the platform's high availability. This maintenance concept reduces crucial equipment deterioration and eliminates substantial repair costs. Vendor preventive maintenance allows the equipment warranty utilization and cheaper maintenance expenses. Since asset health is monitored, opportunistic maintenance is possible and lowering the maintenance cost. Next, the DIP concept is implemented to be feasible for the industrial purposes in this paper's suggested quick and dirty worksheet. The DIP research worksheet can be viewed as an efficient instrument for a stakeholder communicating during an idea study phase to gather inputs, develop possible approaches, and direct further technological exploration on offshore wind substation. The DIP concept is applied. Moreover, well-maintained substation can extend system and platform lifespan. However, aging and its effect may modify equipment behavior, which requires updating maintenance activities. This concept relies on data quality and quantity. Data quality is completeness, compliance, and timeless, whereas data's relevance depends on its timeliness. For instance, early equipment and sensors are replaced by newer and more advanced equipment and sensors with various ranges and readings. Thus, this maintenance concept fails. Even if the monitoring hardware maintains an intact software failure may limit the philosophy's positive influence. Software failures may suppress significant data and the system, preventing effective maintenance or prescriptive algorithm improvement. On the other hand, this has also a negative impact. This maintenance disposition may force companies to use outdated technologies to prevent losing historical data. As mentioned, data drives prescriptive and preventive maintenance. New technology reduces maintenance efficiency. Thus, all systems may need a costly upgrade. That concludes the presentation.